So we're going to talk about the sum of an infinite sum of a geometric sequence, or a geometric series, we would call that. And so this would be a convergent series. So how do I know the difference? Well, a convergent series is one that's actually going to get closer and closer to a number as you add more and more terms to it. And a divergent one is one that starts to go to infinity. So as you keep adding numbers, it's going to get bigger and bigger and bigger. The sum is going to get bigger and bigger and bigger. So one that we might be thinking about is something like if we have 2, 4, 8, 16, right? This is a very simple one. This is just 2 to the n. Well, a sub n is equal to 2 to the n, right? So this one is just, if we start adding these terms together, so if I'm looking for the sum to the 13th term, right, it's going to be a big number. And then if I do the sum to the 17th term, a bigger number, right? And that's going to keep happening. You're going to get a bigger and bigger and bigger and bigger number. Now, it's a little bit different when we have a series that looks, or a sequence that looks like this. If I had 1/2, 1/4, 1/8, 1/16. So what's this one? This one is 1/2 to the n. And so what's happening is each of these terms is getting smaller. Do you see that? This is the biggest actually number that we have in our sequence, and this is the smallest. And if we keep going, obviously, 1/2 to the n, this is going to be a pretty small number if n is big, right? So this one, you can see what's happening here is you're adding 1/2, and then you're adding 1/4, and then you're adding 1/8, and then you get all the way up to here. And what are you going to be adding? Like if this is 1/2 to the 100th, right? This is going to be a very small number, right? This is a very small number. How small? Well, right now, pretty small. As this number grows, as your exponent grows, that is going to get even smaller. So the farther you go down our little sequence here, so if it's 1/2 to the 100 million, right? This is a tiny, tiny, tiny number. So what's happening here is these numbers that I'm adding, if I'm finding the series, if I'm finding the sum, the numbers that I start adding are so teeny, 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 tiny, they're almost zero, right? So if we had 1/2 to, infinitely big, if you could do that, if you were allowed to do that, this would be so tiny, has basically no value, right? Only God would know how big that is. Us mortals wouldn't even be able to tell, right? So the difference between this number and zero. Okay, so what's happening here is if you have a convergent sequence or series here, what's happening is the values that you start adding farther and farther and farther down the line end up being really, really small. So if you take this formula for a finite sum and you think about it in these terms, right? If you're thinking about, infinity, let's pretend we can do that for a moment. We're finding the sum to infinity. Let's pretend that, we as mortals could do that. We're going to go, something like this, right? Well, again, if this is one where our common ratio is less than 1, but of course it has to be bigger than 0, right? If it's between 0 and 1, so like a fraction smaller than 1, like in our example here, what's going to happen here is that these values are going to start to get really tiny the farther we get out. So this guy, if you were raising, a fraction, a 1/3, a 1/8, a 2/16, 2/37, whatever it is, this guy is going to get smaller. Because it's a fraction, right? Raised to infinity, that's going to be small. Or even if it's like 2/7, right? To infinity, going to be small. So any fraction that you can imagine less than 1, you can see how that's going to be a really, really tiny number. basically 0 if our exponent is infinity. So this thing, so r to the infinity basically goes to 0. Does everyone see what we're saying here? So if I'm looking for the infinite sum, and we can only find the infinite sum if this is true, because otherwise this is a divergent one. It's just going to keep getting bigger and bigger and bigger. But if it's a convergent one, meaning this is true, then what's going to happen is we're going to have a sum that looks like this. Basically 0, right? Over 1 minus r. This. So if we have a number that's basically 0, then really what we're going to say is this. So this is just a 1 on top. 1 minus 0 is going to be 0. And so this is going to be our infinite sum. And again, only for a convergent one, because otherwise it doesn't make sense, because this number does not become 0, and another one it becomes this humongous number if the ratio is bigger than 1, right? And so this would be the formula for our finite sum, okay, for a convergent series. And obviously, all you have to do is plug in your numbers. This is a sub 1, so the first term, sometimes you have to figure that out. Sometimes they don't tell you. And we don't put n here anymore, I guess, because n is now infinity. I guess I'm going to cross that out just so we don't get confused, because we're not going to a specific term. We're going to infinity. So I don't have to say sum up to a term. We're saying sum of the whole thing. So I'm not even going to put n there. How's that? Okay? And of course, this is my common ratio, and 1 is a constant. So I think everybody probably can figure out how to plug the numbers into there now. All right, good luck.